Yeah, but
Record day at school, 8:08.
What's up?
Sorry, Rick.
That's okay. Alright. So yesterday we just did a little review of integration topics that we did before break. So that included basic integration rules. It included U substitution, fundamental theorem of calculus part 1, which is just how to evaluate a definite integral. And don't forget how to do it on your calculator. And then those weird problems that have to do with inverse trig. Any questions on any of that stuff? Everybody comfortable with that? Because we're moving on in Unit 6, and it's kind of has a lot of topics. So I want to make sure everybody's really comfortable with where we are. We're good? Okay. So the next thing we're going to talk about then is fairly intuitive. It's just properties of definite integrals. So remember, first of all, FTC part 1, which is, that's not how you spell remember. That's spell remember. Remember, there we go. Remember, it's the integral from A to B of f of x dx equals capital F of B minus capital F of A, where big F prime equals little f, right? That's kind of the bottom line. So big F is the antiderivative of little f. That's FTC part 1 right there. Okay, so there's some important properties that have to do with this that are fairly obvious, I think, and I think you'll be able to get them right away. So the first one is, these are just facts. Let's just write these facts. So the first one is, if you have the integral from a to a of f of x dx. Finish my sentence. What's the answer? Nope. It's 0, right? I mean, you were on the right track. It's f of a minus f of a, which is 0, no matter what. Okay, so if you see something like this on the AP test, and this is the same number as that, this could be any complicated thing that they want to write there. The answer is 0. Don't be fooled. Okay, it's just 0. If you're going from A to A, where A could be any number at all, the answer is 0. That makes sense, right? Definitely should be true. Definitely is true. All right. The second important fact is the integral from B to A, f of x dx, is the negative of the integral from A to B of f of x dx. If you switch the limits of integration, you just get the negative answer. Okay? And that should make sense as well if you just understand the properties of subtraction. This is really f of A minus f of B, right? And this is really f of B minus f of A. And you know that when you subtract two quantities in a different order, they're just negatives of each other, right? Definitely this is a true statement. Okay? So again, that just follows directly from properties of subtraction, since that's what FTC really is, subtraction. Okay, the third thing is if you have the integral from A to B of a constant times f of x, you can just take the constant outside and then take the integral from A to B of f of x. So this just follows directly from the rules for techniques of integration, right? That's the constant multiple rule for So it works for definite integrals as well. Not shocking, hopefully. Definitely, that seems like it should work. The fourth thing also is just totally derived from the rules for indefinite integrals. And it just says that if you have the integral from a to b of f of x plus or minus g of x, what do you think I'm going to write here?
Integral of a to b f of x plus or minus integral of a to b, right?
Exactly. The integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. It's true for indefinite integrals. Why wouldn't it be true for definite integrals? Okay? And then the final property of definite integrals rather is if you have the integral from a to b of f of x dx plus the integral from b to c of f of x dx. What do you think that should be equal to? Yeah, it would be the integral from a to c of f of x dx. And again, it's just because of properties of subtraction. This first integral would be capital F of b minus capital F of a, right? That's what that would be. The second one would be capital F of c minus capital F of b. But if you just look at like what's happening, the F of b cancels with the F of b, you really have F of c minus F of a. But that's what this side is. This is really capital F of c minus capital F of a. So it definitely seems like it should work, definitely works. Okay, so the key here is that this number has to match this number. If those numbers match up, you can just smash them all into one thing, as long as the integrands are the same. Okay, just be careful of that, obviously. But the integrand has to be the exact same function. Okay? So this is almost like the, the transitive property. So does it sort of feel like the transitive property? If you remember what that is. The transitive property says if A equals B and B equals C, then A equals C. You can sort of like skip the middle. It's kind of like that, in a way. Okay? Or it's like, there's a logic law that's like that too. It says like, if you know if P then Q, and you know if Q then R, then you know if P then R, right? Like, if it snows, then I have to shovel. If I have to shovel, then my back hurts. So the conclusion is, if it snows, my back hurts, right? That's the conclusion. It's kind of like that here too. Okay? So these are the important properties you need to know about definite integrals. Now the way that they're used is sort of like in a really weird theoretical way. They're not, I mean, they're obviously, you can use them when you're just evaluating integrals, definite integrals. Definitely, you would use them in that case. But you're sort of forced to use them in more theoretical type problems. Like, for example, they might just give you like a definite definition. Like they might just say, suppose the following things are true. Suppose the integral from 1 to 2 of f of x dx equals -4. And suppose the integral from 1 to 5 of f of x dx is 6. And suppose the integral from 1 to 5 of g of x dx is 8. And then they just might ask you questions about this. Assuming these things are true, evaluate the following, right? So they might just say, find, first, what if they said, find the integral from 2 to 2 of g of x dx? What's the answer? 0. It doesn't really matter what they wrote up here, right? The answer is going to be 0. It doesn't matter what g of x is. The answer is 0, right? What if they said find part B, find the integral from 5 to 1 of g of x? Yeah, you just look at the integral from 1 to 5 of g of x dx, and it's 8, so this is just going to be negative 8. All they did is they switched the limits of integration. So they're just basically like forcing you to consider these rules, okay, in a really like theoretical way. What if you had the integral from 2 to 1 of 3 f of x dx?
Or no, positive.
It would be positive 12, right? Because think about it, this is really 3 times the integral from 2 to 1 of f of x dx. But the integral from 2 to 1 is really the negative of the integral from 1 to 2. So this is the negative of, actually, let me write it this way. 3 times, it would be 3 times the negative integral from 1 to 2 of f of x dx. And since we know what the integral from 1 to 2 is, it's negative 4, this is just going to be 3 times negative 4. So the answer is 12. Okay? What if they said, or D, what if they said find the integral from 2 to 5 of f of x dx? Well, if you look at our given statements, right, we're given the integral from 1 to 2 and the integral from 1 to 5. So how could you find the integral from 2 to 5? Right? That's what we have. We have the integral from 1 to 2 and the integral from 1 to 5 of f of x. What could you do? Well, we could use that fifth rule, that little transitive property thing. We could say this is really equal to the integral from 2 to 1 of f of x plus the integral from 1 to 5. Since the 1's match up, this is going to be equal to the integral from 2 to 5. What's the integral from 2 to 1? Positive 4, right? Because I switched the limits of integration. This is going to be positive 4. What's the integral from 1 to 5 of f of x? 6. It's totally given. So the answer would just be 10 in this case. You kind of see how these rules are used? So if they gave you, this is a typical AP type question, they would give you these given statements, and it would be something like this hard. I mean, which isn't that hard. You just have to know the rules. Yeah.
So for that last one, I wasn't sure if I was right or not, so I didn't say it, but I was gonna say just subtract. Would that kind of be the same thing? Because instead of inversing it and adding it like we did, it would just be subtracting the negative 4 and you'd still get 10.
What? Yeah, obviously 6 minus negative 4 is 10, but I'm just trying to figure out how you reckon with that. So you plugged in, I'm not sure. I don't want to generalize it like that because this is one example. And if you try and say, oh, it seems like this works, I don't really know that that works. And I'm not, maybe it's the way you're explaining or something, but I'm not completely convinced what you're saying is true. Maybe what you're saying is true, maybe it's not, but I would think of it this way, because I just think this is more universally usable, you know what I mean, than trying to make up another rule. You understand what I'm saying?
Yeah.
I'm not saying that what you're saying is not true, but it might not be.
Okay.
Okay? Everybody understand what I'm saying? All right, let's do another problem. What if we had, something like this? What if they gave us, how about this? The integral, so given, the integral from 0 to 3 of f of x dx equals 3, and the integral from 0 to 4 of f of x dx equals 7. And what if they said, find the integral from 4 to 3 of f of x dx? Or better yet, I'm sorry, of 2 f of x dx. Okay, so again, like, let's just take it in steps. This 2 can come out, right? So this is 2 times the integral from 4 to 3 of f of x dx. And then if you look at the integrals that we're given integrals from 0 to 3 and from 0 to 4. 0 is in common, that's good. So what I can do is I can say this is really equal to 2 times the integral from 4 to 0 f of x dx plus the integral from 0 to 3 f of x dx. Does that reasoning make sense? And now I can just make the substitution. This is 2 times, what's the integral from 4 to 0? -7, because again, I switched the limits of integration from what they gave us. And what's the integral from 0 to 3? Totally given, it's 3. So this is just 2 times -4. The answer would be -8. So this stuff isn't too hard, right? I don't think this stuff is very difficult at all. But there's certain things you just have to remember, and they're going to force you to prove that you know it by giving you a problem like this. There's really no way to do this problem without knowing these facts, like just as they are. But it's really abstract, and it's not an actual problem, kind of. You know what I mean? We're not really actually doing a definite integral. They're giving us the definite integral, and we're just doing stuff to it, kind of. So it feels a little weird. There's not really a point to these types of problems other than to prove that you know that how to manipulate them. Any questions about that? That's really all there is for today, is those 5 rules and then just problems like this. Okay, so on mathematics, it's just called properties of definite integrals.
Can I go to the bathroom?
Yeah, sure.
Okay, wait, I think I have a way to better explain what I was asking.
Okay, please do.
So if you look at it like 0 to 4 as a segment,
Yeah.
and then 0 to 3 as a segment, and you're finding, say that's just reversed and you're finding 3 to 4, say.
Yeah.
You know that 3 to 4 is just going to be the segment from 0 to 4 minus the segment from 0 to 3, just for basic math. So could you?
Oh, okay, I'm convinced now. Yeah,
Okay.
That makes sense.
Okay.
That does make sense. And it makes sense because actually what a definite integral is it has a geometric implication like that. It's actually like an area. So if this is the area from 0 to 3, whatever that might mean, and this is the area from 0 to 4, if you wanted the area from 3 to 4, yeah, you just take this area minus this area and you get that area. So yeah, you're exactly right. It's not length of the segment, but you're totally on the right track, and I agree that it works.
Okay.
Yeah, sure. All right, good.